Hello everyone, welcome to assignment 21, and in assignment 21 we're talking about using partial fraction decomposition to evaluate our integrals. And again, I'm not reaching for this first. This is like fourth or fifth on my list of strategies to employ. Certainly, most of the ones we're going to be looking at today, if not all of them, will be done with partial fraction decomposition. Okay. Before we do that, let's have a little bell work. Will you please find the antiderivative? A, b 1 over x squared plus 1. C is the integral of x over x squared plus 1. And d is going to be 1 over x minus 1 squared dx. Okay? So, take a moment to do these four problems. Why don't you pause the video? I really think you should do these problems, and then come back and we'll take a look together. Okay, welcome back. So for this one, I would hope that you'd have ln of x minus 1 plus c. If you need, you can always do a u sub where your u is x minus 1. Here, this is straightforward inverse tangent. Don't forget the plus c. Here, we have another u sub. This time our u is x squared plus 1. So our du will be 2x dx. Well, I see an x dx here, so I'm going to divide both sides by 2 and say that x dx can be replaced with du over 2. So this integral then becomes 1 over u times du over 2, which is going to be 1/2 ln of u, or ln of x squared plus 1. Don't forget the plus c. Okay? And this one here, well, this is the same as integrating x minus 1 to the minus second. You can certainly do this as a u sub, where your u is x minus 1. I'm going to say that the antiderivative here is negative x minus 1 to the negative 1 plus c. Check it out. If I bring down this, I'll have negative times negative for positive. Good. I'll subtract 1 here. That'll be negative 2. Great. Times the derivative of the inside, which is just 1. So there we go. Now, again, the lesson is all of these had denominators. Were all of them ln's? No, not at all. Some of them were ln's. Some of them were inverse tangent. Some were neither ln nor inverse tangent. So please practice, practice, practice so you can delineate these. Okay? How about this one? The integral of 1 over x squared minus 1 dx. What can we do here? Yeah, I agree. The best I can do here is 1 over x minus 1, x plus 1. And no, it's not a u sub. This isn't inverse tan because that's a minus. If I were going to say that this was x squared minus 1 was my u, then I would need a 2x or an x somewhere floating around. Now I don't have that either. So what do we do in a situation like that? Well, this is exactly the time when we want to talk about partial fraction decomposition. I linked a couple of partial fraction decomposition videos from pre-cal on the assignment calendar here. If for some reason you didn't ever do partial fraction decomposition, you probably want to watch that before you come here. Now, having watched those videos and understanding partial fraction decomposition, let's start a little algebraic process. Equals a over x minus 1 plus b over x plus 1. Now I'm going to multiply everywhere by the least common denominator. That's this times this. And that's going to leave me with a times x plus 1 plus b times x minus 1. You could use systems here, but I like using magic numbers. So x equals -1. -1 plus 1 is 0. That goes away. -1 minus 1 is -2b equals 1. And so b is -1/2. I've got another magic number here in x equals 1. 1 minus 1 is 0, so that disappears. 1 plus 1 is 2, so I have 1 equals 2a, or a equals 1/2. Now, a lot of students feel like these things are always either going to be the same or opposites. And the truth is, no, they're not. So don't make that assumption. Assume some other things, like chocolate will make you happy. All right, so what are we doing now? We're going to take these constants and we're going to plug them in for a and b. And so we get 1/2 over x minus 1 plus a negative 1/2 over an x plus 1. And I would be happy with that. So let's now go back to our original question. How do I integrate this? Well, first I factor that denominator and recognize, oh, this is a time for me to use partial fraction decomposition. And that means that this stuff here can go here. That this stuff here can go here. This is the algebraic replacement for that single expression. So let's see what happens when we do that. Now I've got the integral of 1/2 over x minus 1 plus the integral of -1/2 over x plus 1. All right, I'm going to take those constants out. And so I'm going to have 1/2 integral 1 over x minus 1 minus 1/2 integral 1 over x plus 1. And again, I can use a u sub here where u is x minus 1, and I can use a u sub here where where u is x plus 1. And when I'm done in integrating, I should end up with ln of, or 1/2 ln of x minus 1 minus 1/2 ln of x plus 1 plus c. Now, a word of advice. This is fine and beautiful for free response. But on the multiple choice, we're going to see something else. We've got 2 logs joined with subtraction. So I can combine that into 1 x minus 1 over x plus 1. And we have this 1/2 out in front. In fact, that 1/2 can go up there. And so I could literally end up with this integral here is equal to ln of square root x minus 1 over x plus 1, and don't forget the plus c. All right, so in this case, yeah, I needed partial fraction decomposition, and ooh, look, I got some ln's. Not always, sometimes, often, but definitely not always. So let's see what we can do then. How about this one? The integral of 4 over x squared plus 5x plus 6 dx. Again, I'm just going to tell you, this is not anything other than partial fraction. You need partial fraction decomposition here. And in the last problem we did, we had those factors, so I'd recommend doing that first. Come back when you have questions or are done. So we know that this is going to be 4 over x plus 2, x plus 3 equals a over x plus 2 plus b over x plus 3. And I multiply everywhere by the least common denominator. That's just this. It's not this times this times this. Don't do that. That's bad. And so you should end up with 4 equals a, x plus 3 plus b, x plus 2. I've got some magic numbers I can use here in case 1. So x equals -3. I'm just going to make that disappear. -3 plus 2 is -b equals 4, and so b equals -4. I can also plug in x equals -2 Negative 2 plus 2 is 0, so that goes away. Negative 2 plus 3 is 1. A equals 4. Okay, so I can replace this integral with 4 over x plus 2 minus 4 over x plus 3. All right, they both have a 4. I could certainly take those 4s out. And now I have these. So 4 ln x plus 2 minus 4 ln x plus 3. And yes, I can condense this. I could factor out a 4 from both of them. Then I would have 2 logs join the subtraction. So I can write 4 ln x plus 2 over x plus 3. And I could even pull that up here to get ln x plus 2 over x plus 3 to the 4th. And please don't forget your plus c. All right, well, I'm hoping that's feeling like a little not horrible. How about this one? 2x minus 2 over x squared minus 2x plus 1 dx. Why don't you write this down, pause the video, and give it a try. Come back when you have questions or when you're done and want to check your answer. Okay, welcome back. You didn't try and do this with partial fraction decomposition, did you? You should be going down that list. Is this a derivative I remember? No. Is this a u sub? Oh, I see a function and the derivative of that function. This is a u sub. So u equals x squared minus 2x plus 1. Du then is 2x minus 2 dx. Why, I have exactly that. So this becomes 1 over u du. Well, that's easy. That's just the ln of u, ln of x squared minus 2x plus 1, and don't forget the plus c. Now, what if you had thought to use partial fraction decomposition here? I mean, I wouldn't. It's a pretty fast u sub. But does this factor? Sure, x minus 1, x minus 1. So what's the setup for this? Well, the setup is a over x minus 1 plus b over x minus 1 squared. And when we multiply everywhere by our least common denominator, x minus 1 squared, we end up with 2x minus 2 equals a times an x minus 1. And when I multiply here by x minus 1 squared, they're going to cancel. I'm just going to have a b here. So I actually like systems here. So I'm going to have ax minus a plus b equals 2x minus 2. I'll set the x stuff equal to each other. Now I'll get 2x equals ax, so a equals 2. And then I'm going to take this not x stuff and set it equal to this not x thing. And so we have negative 2 equals negative a plus b. We know a is 2. Well, that's going to mean b is 0. What's up with that? Well, I'll show you what's up with that. Hey, did you think to factor in the top? Oh, and look what we had in the bottom. Oh, look, if this thing, simplifies, and it simplifies exactly to what? 2 over x minus 1. 2 over x minus 1. That's interesting. But wait, I thought we did this with a u sub. What happened? Well, let's look at it again. X squared minus 2x plus 1 was our u. And we said, okay, du is going to be 2x minus 2 dx. Great, I got all that. So this is 1 over u du. And that meant for us ln of u, x squared minus 2x plus 1 plus c. Great. Now, this doesn't look like 2 ln x minus 1. Or does it? Hey, so isn't this the same as x minus 1 squared? And in the presence of that log, can't I bring that down? And so I'm going to get 2 ln x minus 1, which I believe is what we have when we did it with partial fraction decomposition. Yes, don't forget the plus c. So, yes, these were the same. No, they definitely didn't look the same. Okay, that was exciting. How about something less exciting? Maybe excitement isn't what you want as a math student dealing with integrals with partial fraction decomposition, but instead you're looking for something that won't kill you. Crawl out from under the bed at night and take... Yeah, no. Okay, so is this a u sub? Well, the derivative of this is 2x minus 2, and I don't have that there. So I think I'm going to look at a over x minus 1 plus b over x minus 1, don't forget squared. I multiply everywhere by my least common denominator, which is this, because that's this, and I end up with 3x plus 4 equals a, x minus 1 plus b. Great, I've got a magic number. I could use x equals 1. Problem is I've got two constants to find and only one magic number. So I figure I'm just going to use systems to figure this out. I'll set the x to the first stuff equal to the x to the first stuff, and that gives me that a equals 3. And I'll set the I don't have an x equal to the I don't have an x. So 4 equals negative a plus b, and we know that a is 3. So negative 3 plus b, and b must equal 7. That's really a 7. So this becomes a 3, and this becomes a 7. And now we can start doing our calculus. Now we're saying that this integral, which we couldn't integrate, can be broken up into these two integrals, each of which we can integrate. So I've got this for the first one, plus this, better yet, for the second one. Here, I'm going to have 3 ln x minus 1. And then here, the antiderivative here, this is not ln, this is add 1. And so I should have minus 7 x to the minus 1 to the minus 1. And don't forget the plus c. Look, that's not an ln. Not everything is going to be an ln. Stop trying to force that to happen. It's not going to happen. Okay? Okay. So, we move on. How about this one? The integral of 12x plus 5 over 6x squared plus 5x minus 4 dx. Again, I think, oh, u sub 12x plus 5. I've got 12x plus 5. Oh, well, that's very interesting. Huh. Well, let's use a u sub then. U is 6x squared plus 5x minus 4. Therefore, du will be 12x plus 5 dx. So this can be written as 1 over u du. That's cool. And so we get ln of u plus c. And let's plug that u value back in. And so we're going to have ln of 6x squared plus 5x minus 4. And don't forget the plus c. Nice. That wasn't so bad. Should I do this with partial fraction decomposition? Well, let's see. This is going to be 3x, 2x. I'm going to put 4 into 1, and that's going to be plus and minus. Yeah, I got two factors here, and none of them cancel with the thing on the top. So let's try that. So I've got that that's equal to a over 3x plus 4 plus b over 2x minus 1. Well, let's see if we can find that, that a and that b, given that 12x plus 5 equals a times 2x minus 1 plus b times 3x plus 4. Okay, I've got two magic numbers. If x equals 1/2, this disappears. 1/2 times 12 is 6, 6 plus 5 is 11, and I'm plugging in 1/2 for x. So this is 3/2 plus 8/2 is 11/2, b. So if I multiply both sides by 2 over 11, I get that b equals 2. That's from using this magic number. Well, let's use this magic number. X equals negative 4/3. So I plug negative 4/3 in here. The 3's cancel. I have minus 4 plus 4 is 0, and 0 times b makes that disappear. If I plug my negative 4/3 in here, I'm going to have negative 8/3 minus 3/3 is negative 11/3. And over here, when I plug in negative 4/3, the 3's cancel. I have negative 16 plus 5, which is negative 11. And I believe I end up with a equals 3. Okay, so how does this get rewritten? Well, that's a 3 up there, and that's a 2 up there. Cool. Let's go further. So I'm going to split this into two integrals. I'm going to pull those constants out. Well, wait a second. So if u here is 3x plus 4, isn't du going to be 3dx? No, 3dx. There it is. So this is the integral of 1 over u du. And what about over here? What if I do a u sub over here, where u is 2x minus 1? And wouldn't du be 2dx? Huh, I have a 2dx. So this is plus the integral of 1 over u du. So here, ln of u plus integral here, ln of this u, 2x minus 1. And don't forget the plus c. Hey, two logs joined with addition, that's multiplication. So I have the ln of 3x plus 4 times 2x minus 1. All of that is inside the ln, and don't forget the plus c. All right. Okay, and by the way, if you FOIL, that's what we got last time. So I do sometimes have some options on what to do and how to do it. Okay, let's just look at a couple of more of these. So how about this one here? Integral x squared plus x minus 1 over x squared plus 1 times x dx. Now some students say to me, oh look, Mr. Duke, the degree on top and the degree on the bottom are the same. Should I do long division? And why do I say no? Right, because when you distribute this x to these places, the denominator's degree is in fact larger. So no, this isn't a long division situation. I've given it to you in factored form so that you could write ax plus b over x squared plus 1 plus c over x. Yeah, that's called case 3 when you go back and watch that video. This is case 3 where we have an irreducible, i.e. I can't factor it with real numbers, situation. All right, so I multiply everywhere by this. This is the least common denominator. And I end up with x squared plus x minus 1 equals ax plus b times x plus c times x squared plus 1. Now, magic numbers, what do you think? Well, nothing's turning that into a 0. X equals 0, we'll turn that into a 0, but I got 3 constants to find and only one magic number, so now I'm using systems here. Ax squared plus bx plus cx squared plus c. And let's group things together. Let's take all the x squared stuff. X squared equals ax squared plus cx squared. And if I divide everywhere by x squared, I get 1 equals a plus c. Now let's take all the stuff with x to the first. X equals bx. Oh, well, doesn't that mean just that b equals 1? Sure does. And then over here, I've got not x with not x. So negative 1 equals c. So I can take this negative 1 now and plug it in there, and that tells me that a equals 2. So this becomes a 2, b is 1, and c is negative 1. All right, so now we've broken down this one integral, this one fraction into these two fractions. Let's integrate each of them. So, is this a u sub? Well, the derivative of this is 2x, but no. Hey, you know what this is? This is, let's split this into two fractions. One of them will be 2x over x squared plus 1. The other one is going to be 1 over x squared plus 1. And don't forget, we still have 1 over x here. Well, what do we have? This is a u sub, because here's the derivative of this. This is inverse tan, and that's ln. Hot dog! We got lots of practice. U equals 2x dx. U equals x squared plus 1, and du equals 2x dx. So this is going to become 1 over u, nice, plus tangent inverse x minus ln of x, don't forget the plus c. This integral of 1 over u, well, we know that's going to be ln of u. Our u is this, and so we have ln of x squared plus 1. Look at all the different bits there. No, really, I split this up into two fractions. So I could do the u sub, so I could have the inverse tan. Yeah, you might want to do that one again, huh? Okay. Boy, I really like that one. That's a great problem. Next, how about you do this one? 2x squared minus x minus 1 over x squared plus 1 times x minus 2 dx. Pause the video, give it a try, come back when you're done or have questions. I started with partial fraction decomposition, ax plus b over x squared plus 1 plus c over x minus 2. And when I multiply everywhere by my least common denominator, I'm going to have 2x squared minus x minus 1 equals ax plus b times x minus 2 plus c times x squared plus 1. Well, here I see two magic numbers, x equals 2 and x equals 0. So I could either do this with systems, or I could use two magic numbers and one not so magic number. And I think I want to demonstrate that. So when x equals 2, 2 minus 2 is 0. All of that goes away. 2 squared is 4 plus 1 is 5. So we've got 5c. And I'm plugging in x equals 2 here. 2 squared is 4. 4 times 2 is 8. 8 minus 2 is 6. Minus 1 is 5. And so c equals 1. Fabulous. That was with x equal to 2. What about x equal to 0? Well, that's going to go away. and that's going to go away, and that's going to go away. So we have minus 2b plus c equals 0, 0, minus 1. Okay, we know c is 1, so let's plug that in. Minus 1 equals minus 2b plus 1. And that, when I bring that 1 over, is going to be minus 2 equals minus 2b. And so we know that b equals 1. Finally, I need a not-so-magic number. Now, what do I mean by that? Well, I've used up all the numbers that will turn things into 0. So literally, I have to pick any other number. I like 3, because 3 minus 2 is 1. So when x equals 3, I get 3a plus b times 1 plus 3 squared is 9 plus 1 is 10c. On the other side of the equation, when I plug in a 3, 3 squared is 9 times 2 is 18. 18 minus 3 is 15 minus 1 is 14. So I know all this is equal to 14. But I also know that b is 1 and that c is 1. So I'm going to subtract 10 from both sides, and I'll have 3a plus 1. 3 equals 3a, a equals 1. Now, remember, all of the work we've just done was the algebra to get us to the place where we could integrate. This I can integrate. So, will you please do this integral, find the antiderivative here. So, that should be pretty straightforward with ln of x minus 2. Don't forget the plus c. Yeah, but what about over here? No, it's not inverse tangent because I have more than a 1 up there. No, it's not quite a u sub because I've got this. However, if I split that up into x over x squared plus 1 over x squared plus 1 plus that, then yeah, this is a u sub where u is x squared plus 1. And so du is going to be 2x dx. I've got an x dx here, so I'm going to divide by 2. So this is going to be the integral of 1 over u du over 2, or 1/2 ln of x squared plus 1. And that's this part. This part is just inverse tangent. Now we've got our minus ln x minus 2 and plus c. Ta-da! There you go. Partial fraction decomposition, even with case 3. Okay, so the last things I want to talk to you about are improper. Yeah, we saw some of these in the last 2 years on the AP exam. Didn't think that was part of the curriculum, but there it was. So x squared plus 3x plus 2 dx. Hey, look, the degree of the top is bigger than the degree of the bottom. When they're either the same degree or the top is bigger, I'm going to do long division. Plus 3x plus 2. Long division before I would even consider partial fraction decomposition. No, really. 2x to the third minus x squared plus x plus 5. What do I multiply that by to turn it into that? 2x, 6x squared plus 4x. And don't forget to subtract. Minus 7x squared minus 3x plus 5. What do I multiply that by to make it be this? Negative 7 minus 21x minus 14, and I subtract. It's going to be 18x plus 19 plus 18x plus 19 over x squared plus 3x plus 2. All right, cool so far, but wait, there's more. So this can be replaced with 2x minus 7 plus 18x plus 19 over x plus 2, x plus 1 dx. So this, the antiderivative is x squared. This, minus 7x. This, partial fraction decomposition. We've got 18x plus 19 over x plus 2, x plus 1 should equal a over x plus 2 plus b over x plus 1. When I multiply everywhere by the least common denominator, I get 18x plus 19 equals a times x plus 1 plus b times x plus 2. Look, two magic numbers and only two constants to find. Piece of cake. If I make x equal to negative 1, this goes away. Minus 1 plus 2 is 1b. And over here, if I make x equal to negative 1, I have negative 18 plus 19, which is 1. So I know that b is 1. Now, what about plugging in my other magic number? X equals negative 2. Negative 36 plus 19. I believe that's negative 17. Yes, negative 17. And I'm plugging in negative 2 plus 1 is negative 1a. And here when I plug in a negative 2, I get 0 times b. So a equals 17. Okay. We plugged in a negative 2. It's negative 36 plus 19. That's negative 17. No, no, no. Yes, yes, yes. Okay, so I'm going with that. Which means now, when it's time for me to integrate this part over here, I'm actually integrating 17 over x plus 2 plus 1 over x plus 1. And so my final answer, I can write it over here. I believe my final answer then is x squared minus 7x plus 17 ln x plus 2 plus ln x plus 1. Well, and don't forget the plus c. I know, I feel like I'm really doing some stuff here in these problems. All right, why don't you try? Doing one of these improper ones? How about x to the third over x squared plus 4 dx? This should be pretty straightforward. Let's see how it goes. 5. Oh, sorry. You were coming back. You're back. Well, welcome back. Because the degree of the top is the same or larger than the degree on the bottom, we're going to do some long division. And what do I multiply that by to turn it to that? Plus 4x and subtract. Minus 4x. Okay. No. So plus negative 4x over x squared plus 4. Great. So this thing that I couldn't integrate is equal to x squared plus 4. Fabulous. Let's split this up into two integrals. We're going to have the integral of x minus the integral of 4x over x squared plus 4 dx. I see part of the derivative of the denominator here, so I'm going to make u x squared plus 4. Du will be 2x dx. There's a 4x. So, if I multiply this by 2, I can have 4x dx, so I'd better multiply this side by 2 as well. All right, so then this integral can be rewritten as the integral of all of that is 2 du, and here I've got u in the denominator. I can pull out that constant, 2 integral 1 over u du, Well, that's just ln of u times 2. ln of times 2. So this with the antiderivative of that. All right, so the antiderivative of this is x squared over 2 minus 2 ln x squared plus 4, and don't forget the plus c. All right, nice. Well, maybe that's not as bad as I was expecting it to be. All right. Well, fabulous. So there's our quick look into partial fraction decomposition to help us with integrating. I hope this was useful, and I look forward to seeing you in our next video, where we will have a cyclone of integrals to do. Yeah, let's wear the fire hat for this one. See you soon.